All right, so the last thing we did is we talked about the Hilbert basis theorem, polynomials, the analog for power series. I'm going to get more into this later, but let R domain then in Rx and by the way, I didn't state it this way, but this is an if and only if actually. In a following sense. R is numerable domain if and only if an RS is prime. So, of course, one of the things that you can do, we haven't really defined degree formally yet, but we're going to, is you could start trying to convince yourself that X is in fact a prime element or it's a prime ideal. But I think the sort of the slickest way to do this is consider the homomorphism P from Rx into R, given by phi of P of X, P of 0. Right? It's easy to verify that this is a surjective ring homomorphism. And so, Rx mod curl phi is isomorphic R. R is a domain, and curl phi is easily seen to be the ideal generated by X, right? The stuff that goes to 0 has that factor of X in it. Therefore, X it's also easy to see that R is not a domain. Well, this is still the kernel of that map, and so that's where you get the if and only insert there. Okay. Definition. So here I'm going to define the notion of degree formally. Let R be a domain, or actually let R ring. Why is that domain? I just must have been a groove or something. And f of x is a n x n plus 1 minus 1 and 1 x 0 with and that's an important caveat where a n is not 0. Then we say the degree of f of x, degree of f is equal to n. And formally, of course, this definition begs the following question. Jim, what if all the coefficients are 0, right? Then we will say the degree of f. Sometimes I might say it's undefined if I'm lazy. You can also define it. And I'm gonna update this. So proposition.
Degree of 0.
What's that?
Is that degree of 0?
Yes, sorry. Degree of. Thank you very much. So, proposition. 225. Let R be a ring. And F, G are polynomials. The coefficients in R. We say that for A, degree of F of X plus G of X is less than or equal to the max degree F degree. So intuitively, here's what can happen. When you add two polynomials, their degree certainly doesn't get bigger, right? Bigger than the max, right? But you might have the leading terms accidentally cancel out, dropping the degree down. And notice this incorporates the negative infinity quite well. B, the degree of FG is less than or equal to the following holds in the domain. And so apparently I'll let this as an exercise, but let me kind of run through this a little bit. For A, well, say degree F equals N and degree G equals M. Then if you look, so F is equal to A N X N plus 1x 0, and G is equal to B M X M B1x plus B0, where A N B M are not 0. And I'll make a further observation that goes beyond what I've said here. If N is bigger than M, then degree of F plus G equals N. So what I can conclude from this statement is if you add two polynomials that have different degrees, then you will actually have an equality for the max. The only time that this can screw up for you is if you add two polynomials of the same degree, and in which case, even in the equality situation, then the leading coefficient would be an plus bn, which if it's not 0, then you get equality again, and if it is 0, then that's why we need the inequality. For B, we use notation from A. Notice that FG is AN BM x to the n plus m plus A0 B0. Right? And that's really kind of all I need is the leading terms there. Note, if R is a domain, degree F plus degree D equals degree FG. Because if AN and BN are non-zero, then there's no way that's going to be 0. And if not, we have the desired spread of that equals. because the degree of F you could draw, even to negative infinity in the extreme case. Actually, it's interesting to see that there's actually a theorem, which I don't think I'll get to, but I can't resist this, is if you have a polynomial that is a zero divisor, so suppose you have f of x and you can multiply it by some of the g of x and you get z, then you can actually multiply by a constant, a non-zero constant. That's actually a theorem. So that's kind of neat, right? Because when you multiply the polynomials, you get this kind of big, huge collection of terms. Turns out that if you can ever do that, you can actually collapse it down and multiply by non-zero constant, which is, I don't think that's obvious, right? So you might think about why that's true. And I'll give you kind of a funny factorization. This is one of the 17 reasons why I hate zero divisors. So if you look at this, this is 6x squared plus 9 and 4 is 13x plus 6. But of course, this whole thing is mod 6. All right, so that's 0, 0, 1. So notice that every coefficient of this is a zero divisor, same with this, and the product has only unit coefficients, right? So notice that we have the first theorem that we had today was that over an integral domain x is prime. Here it's not even irreducible, right? And in fact, this is kind of fun, but when you talk about factorization, I can't resist this one because this is really what made me angry with zero divisors, is it is possible that, so there's a very famous theorem that, so you all know what atomic means. It means everything can factor into irreducibles, right? So suppose that you have a ring that is atomic, so everything can factor into irreducibles, right? Well, all kinds of familiar examples. See, any Noetherian ring, whatever you like, right? Is it true that if you have a domain that is atomic, that its polynomial ring is atomic? Well, I wouldn't expect a quick answer. I mean, it sort of seems obvious, right? So here's what you think, right? Okay, take a polynomial, and what can you do? You start factoring it, and this is over an integral domain. So you start factoring it, and you'll reach some point where you can't factor the degree stuff any lower. Because even over the quotient field, you can factor this down and do it worse product linear, right? So now you've reached a step where the pieces, parts of your polynomial, you can't take them down in degree anymore. So what's left? All you can do is start jerking constants out. And since it's atomic, that process has got to stop, right? Nope. In fact, there are examples of rings where you can factor everything into irreducible. Polynomial ring, this doesn't work, which is a very, very kind of strange set of affairs. In fact, how it works on polynomials, I don't think it's really extremely well. There's all kinds of theory. I will say this with a caveat, though. The paper that's in is by a mathematician who is very good with examples and stuff. And everybody that I have talked to that has read that paper very carefully said, I didn't really understand it. So it makes me, so if any graduate student, if you're like masochistic or something, wants to do, I'm happy to be able to put you in an insane asylum. However, there's something even weirder too. There is an example of a ring that has zero divisors. Okay, so now you've got zero divisors. And this ring has no irreducibles at all. Right? So anything that you could take always breaks down a little further. Right? But its polynomial ring is atomic. So when you do it over the polynomial ring, so now the constants can break down, but they must break down into polynomials. That's when I quit. That's it's too weird to call it TV. So here's a nice corollary of this last bit. Corollary. And this is very much in contrast to the power series ring, which we talked about and we'll formalize a little bit later. Let R a domain so let R be a domain and UR be the units of R. I will use that notation a lot, I think, in this course. Then the units of Rx, units of R. So this one's worthwhile showing. And actually, this is very important. Actually, I've done some stuff in factorization recently, talking about things like ACCP and atomic and so forth. This is incredibly useful. The fact that this is one of the things, in my humble opinion, that make polynomials a useful thing or a useful ring extension is when you pass from the ring, polynomial ring, it doesn't generate new units, right? And so for certain things, that's a very convenient thing to have. Certainly, UR is contained in URS. Of course, that all anything that has an inverse in R, that inverse big in R is also in RS, so no problem there. And the rest of it is just a degree on it. So here's why it's a corollary. Now let f of x be on U Rx, so it's a polynomial, it's a unit. So f of x, g of x is equal to 1, sum g of x and R of x. And now just slap a degree on this. And of course, the degree of polynomial 1 is 0. And since we're in an integral domain, this is equal to degree f plus degree g. And each of these degree f's are, of course, greater than or equal to 0. No negative infinities allowed here because their product has to be 1, right? Therefore, degree f equals degree g is 0. So f is in UR. Okay. Any questions on that? By the way, anybody know what's the analog for zero processors? I know what it is. All right. So suppose, okay, so now here's what happens. The units for an integral domain, the units of the polynomial rate are exactly the units of R. It's a little bit more general with zero. Anybody know what it is? This sounds like maybe a good homework problem proof. It's not too difficult. But see, can you use the force and see what it is?
A unit constant plus maybe the full volume transfer coefficients are 2 dividers. So something like that.
Okay, good start. Okay, you notice that the constant term had to be ding ding ding. And what about the rest of them?
The coefficients being 0 dividers.
Up the voltage just a little bit. Well, so what's a class of zero divisor that's stronger than your garden variety zero divisor? There you go. Yeah, I think what it is if I remember right, the constant term has to be a unit and the rest of the coefficients have to be null. which is a nice generalization of this, right? Because in an integral domain, the only nilpotent is 0. Okay. This is another one worth recording. We'll also record the analog power series after a bit. Right, proposition 228. Let R be commutative with identity and I a proper ideal. Then I think this notation is pretty suggestive, but I'll write this out anyway. What do I mean by I bracket X? I steal the notation from polynomial. This is just polynomials where all the coefficients are in I. So this is, so it looks like this. So for example, if I is the ideal generated by 2 in the integers, and this would just be all polynomials with equal coefficients. And I comma X. This is, of course, the smallest ideal in Rx that contains all the elements of I and also the element X. Are ideals. R of X. And what is more, one Rx modulo Ix is isomorphic R mod I X. And 2 Rx modulo Ix is isomorphic. Oh, anybody will guess this one? Right. Let me be sloppy and show you my intuition. X is 0 now, so this should be R mod I. So I is prime if and only if Ix respectively I comma X. And if I is maximal, so is Ix. Let me point out a couple of things before we get rolling on this. The first one to point out, I think, is Ix, this thing right here, is all polynomials, all of whose coefficients are in I, right? This one, you can think of this. These are all polynomials whose constant term is an I. And after the constant term, you've got complete willy-nilly freedom, right? So in a certain sense, this is kind of most of the polynomial thing, right? Because everything from the linear term on up, you got complete freedom with what to put in that ideal, right? So that's my first observation. Right. All in I, only the first in I. So this part of the proof here, I is prime. Notice that if I is prime, and this is an integral domain, forcing that to be an integral domain, forcing Ix to be prime. And conversely, again, if I is prime, that's a domain, and so I comma X must be a prime ideal. And finally, if I is a maximal ideal, that means this is a field, meaning that I comma X is maximal. Notice for polynomials, the converse is true for the last one. It is not true well, no, let me restate what I was saying here. Every ideal, I comma x, if I is maximal, is maximal ideal polynomial. But not every maximal ideal polynomial ring will be of this form. There are others, right? Let me give you a silly example. Before we go into this. Yeah, this is some silliness here, but it generalizes quite well. Take the field F. How many ideals are there? Zero, right? There's just zero ideal, and zero is maximal, right? Notice that 0, x is a maximal ideal of this, right? But this thing is chock full of maximal ideals that are not the ideal generated by x. For example, the ideal generated by x plus 1. And then you might have other exotic things depending on what the field looks like. In fact, you will always have infinitely many maximal ideals in here for the following reason. Number one, the field F may be infinite, right? And if it's an infinite field, then the ideal x minus alpha is maximal for every alpha, right? If it's not an infinite field, it's a finite field. And there's a theorem that you may or may not have seen in 8520 or in your other encounters. But anyway, if you have a finite field, then you can't do my trick before. But it turns out for a finite field, there's an irreducible polynomial of every degree. Well, there certainly is there's an infinite for a finite field, there's an irreducible polynomial of any degree of that field. So once again, you have infinitely many maximal ideals. Okay, so let's see. Let me kind of sketch this part of this. I will leave the fact that Ix and I comma x are ideals to you all. It's easy to show their ideals. For one, consider phi from Rx into R mod I x. I love first isomorphism. Okay. How is this going to work? I guess it's best to do it this way. Let's say AIXI equals 0 n is the polynomial AI plus I. So in other words, the way this homomorphism works, it's something like this notation. If you've done some number theory, like modular, whatever notation you like. Or by AI bar, I just mean the coset reduction. It's easy to verify that this is a homomorphism. That's, more pain than it's worth, right? But this is pretty easily a homomorphism. And it's also pretty clearly onto, isn't it? Right? Because whatever cosets you want to build up your polynomial, you've probably got, in fact, infinitely many choices for every maybe, but you've certainly got at least one choice for every representative. Right? And so notice that phi is a ring epimorphism. So this means that Rx modulo the kernel of phi is isomorphic to R mod I x. But what is the kernel of phi? What does it mean for this to come out to 0? This means that AI plus I equals 0 plus I, which means that AI is in I for all I. Therefore, the kernel of phi is Ix. And so that's exactly what you wanted. This mod the kernel, which is Ix. The other one, I'll just start it and let you finish. The other one's sort of easier. Two, let's pitchfork, go from Rx into R. A pitchfork. Any guesses what we should do here? Right, just take a constant term. This is in R. And so pick any element of R and build a polynomial. Well, in fact, pick any element of R and take that to be your polynomial, and you're covered. This is pretty easy to see that it's a homomorphism, and the kernel is the ideal generated by X. And so there you go. Well, I should say, I got too excited here. There we go. There, that's the there. Now the kernel of this, kernel of pitchfork is the set of P0 such that well, the set of Px such that P0 is in I. Right, because what do you need to do to go to zero via this map? Where I'm not doing just P0, I'm taking its equivalence, or I'm taking its coset and all mod I. So what does it mean for this thing to be zero? It means P0 is an I. So what does it mean for a polynomial to be in the kernel? It just means that its constant term is an I. So this is I comma X. There we go. Okay. Any questions? Okay, so now let's do a little bit in the realm of power series. Let me say something about my experience with power series. Is there's a bunch of theorems that, okay, the same thing happens with power series, and proof is almost exactly the same. If it's different, if you get the same result or similar results, then sometimes it's easier for power series than polynomials. That case is on the set of measure 0, right? It's usually the polynomial result is usually easier than the power series. And I'll give you one or two exceptions, but the theorems are usually nicer for polynomials and power series. But the first one, let R be a ring, community of identity. I'll say this in more generality. Then R is a domain if and only if the ideal generated by X in R powered X. And the proof of this is basically the same. Just do a homomorphism with the kernel. Here's another analog. So this theorem, essentially same as polynomial. Here's another one that's the same. If R is a domain, so it but I'm going to look at this proof just for a minute. Let's suppose R is a domain. What does that mean? Near group of identity, no non-zero zero value, right? Well, okay. First of all, I need R power x at one. No problem over there, because the one in our functions is, under our definition of power of multiplication, one functions as the identity. So that's not a problem. Really what we need to do is it suffices our power x has no non-zero zero values. Now, here's my dilemma, though. The way we proved this was by using degree for polynomials. That ain't gonna fly. Any ideas? You don't have to go all the way to Chicago for this. We look at something called the order of F, ORD. Well, so this is sort of analogous to degree, only because this is power sheet, we've got to take it to the other end, right? Suppose f of x is non-zero. Just like you have to make some concessions when you're discussing degree of the zero polynomial, we also have to make concessions when discussing the ORD of f. Power sheet. I'm gonna assume that f is not zero here. But you can also, just like you do the wacky, I think you can define the order of the infinitive, but we'll see. So what do I know about f of x? Well, f of x is a power series and it's not zero, so it has to have at least one non-zero coefficient, right? Suppose this is the smallest. Okay, flies off with a n, not zero. Then ORD f is equal to n. So instead of being the highest degree term that appears, it's the lowest degree term. So for example, if the power series has a constant term, then the order will be zero. Okay, just for fun, as kind of a little side note before we move on, just like degree order has some properties too. See if y'all can help me out. So here F and G are power series. What are you supposed to happen to the order here? Yeah, right. So when you add two, so what can happen is you're looking at the smallest degree terms. It's actually the minimum of those two, unless you get unlucky and they add up to zero, and then it can be bigger. So this is actually what greater than or equal to min or and just like with polynomials, you get equality if the orders are actually different. Everybody okay with that? So notice it's kind of dual, if you will, to what happened in polynomials, because this is a min instead of a max. What about ORD? What about ORD FG? What happens there? Well, you multiply those two smallest terms, and that will give you the smallest term of the next one, unless they multiply together to zero, in which case the order might be bigger. So this is greater than or equal to 4F plus 4G. Right? And equality. Well, an R is. Everybody agree with that? And so. To make this compatible, how do I have to define it with a zero? Let's assume that I don't want to just say undefined and flake off like that. Or we'll make all this work. This one needs infinity, right? Okay, so with that in mind, we need to show that this has no non-zero zero divisors. So suppose that f of x and g of x are not zero, then or f equals m or g equals n, and hence or fg equals m plus n, which is strict less than infinity, so fg is not zero. There you go. So it's a integral domain because the product of two, because it's got one, and the product of two non-zero elements of the power series is still non-zero. Okay, so any questions? Yes.
We have just inspected the constant term and multiplying them, notice that that's non-zero because R is a domain, and then used deduction.
I'm sorry,
So we have just multiplied F and G together, and then notice that the constant term is non-zero because R is a domain.
well, let me make sure I'm understanding this right. Of course, for a power series, the constant term doesn't have to be zero.
Yeah.
Right.
Like we had non-zero constant terms and then multiplied them together.
Well, right. But this, so there may be we may have a terminology thing. This is not a constant term because it appears at the. And so I think I'm misunderstanding your question. So,
I don't know.
I mean, if you have a domain, then there's certainly all kinds of power series, like for example, X that have zero constant, right? But are you saying like,
If you define,
maybe what you're saying is you can inductively take out powers of X and just argue like that? Maybe?
yeah, if you define F of X to be A0 plus A1X plus A2X squared on, and then G of X, we define similarly. And you multiply them together.
Yeah, okay, so one of the things that you could do, since this is a domain, is you could make some kind of argument that you could pull out Xn. And then you could make an argument that you could forget Xn, and you could start with An being constant term and do it like that. So, this is actually one of my favorite theorems. This past two theorems, polynomials power series, same kind of thing. This one is a little bit different. Theorem. Oh, yeah. By the way, with polynomials, I had a caveat on, we had the theorem that said URX is equal to UR, but I said it's a domain, and then I said you can generalize that if you want to this business about constant term being unit nilpotence. Here, I don't have anything. I only have the R as a commutative for the identity. What do the units look like here? Anybody know? This is crazy. power series. And of course, it's wildly improved polynomials. The units are precisely the same here. So what this theorem is telling you is there's a lot of units in the power series, because all you got to do is make sure the constant term is a unit, and you're good to go. All right, you're good to go. So in particular, so here's the corollary. You could certainly have, if you have a commutative ring 1, you could have a polynomial ring that only has one unit, right? Because if R only has one unit, then, you know, like for example, F2, right? Something like that. Or you can have polynomial ring that has a small number of units. Power series always have uncountable units, right? Because basically you can think of all the coefficients. For example, it has uncountably many units of this form. Make U 1, and the rest of the coefficients, you can choose zeros and ones for it, right? So there's uncountably many even in this form. Let me give you a sloppy proof of why this is true. This is like, I call this high school division, sort of, and this is what makes power series different. So if you have U plus X at X, you can factor this as U times 1 plus X F with a chateau X, right? Just by pulling the unit out of everything, right? And so if this is invertible, then the whole thing is invertible. Everybody agree with that? So I might as well start with 1. I can't believe I'm not do this on YouTube, because it's like, you know, it's totally sloppy. But I think it gives you the idea of the proof. If you want to divide this into anything, you'll see quickly that this unit is what makes this machine go. Because B0, you get B0 plus A1 B0X plus A2 B0 X squared plus. And just like you're in high school, you would subtract like you're doing long thing. B1 minus A1 B0 X plus B2 minus A2 B0 X squared and so forth. Right? Now, can you divide this into this? Yes, of course you can, because it's freaking 1, right? So this is B1 minus A1 B0 X. And you do this again, B1 minus A1 B0 X. And every time you bring down, you can always get, because this thing's always going to be in rings, subtraction, you can always build this. And you never have to stop because it's a power series. And so that's why this is essentially all invertible. Now the formal proof, you can actually basically build the coefficients of the inverse inductively. Right, that's how you can formally do it, but I think this gets that. Okay, any questions on that? Any questions? All right, well, think about the math club today. And if I don't see you, y'all have a good weekend. We'll see you on Monday. Good.